So here's a huge question for you. How do we find a single objective reality when there are literally an infinite number of ways to describe it? It's one of the deepest questions in all of physics, and the answer, well, it might just lie in the work of a 19th century mathematician you've probably never heard of. This is the story of the invariant gap.
You know, when we think about the giants of science, we usually boil them down to one single defining breakthrough, right? For Newton, it's gravity. For Einstein, it's relativity. For Darwin, it's evolution. It makes for a nice, clean story.
But then you get to a guy like Elwin Bruno Christoffel, and he's a bit of a puzzle, because on the one hand, his work is absolutely fundamental to the language of modern geometry, the math we use to understand curved spaces. But on the other hand, he came up with a totally groundbreaking theory for how shockwaves propagate. Two completely different fields, two massive contributions.
So what's the deal? Were these just two brilliant but totally disconnected ideas from a genius mind? Or was Christoffel secretly working on one single profound program this whole time? Okay, to get to the bottom of this, we first have to wrap our heads around the fundamental problem he was wrestling with. It's a problem we can call the abyss of descriptions.
Just think about it. You've got one single physical event happening, but you could describe it with your standard XYZ coordinates, or you could use polar coordinates, or you could invent any number of twisted, custom-made systems you want. The underlying reality never changes, but your description of it does, and that creates this, well, an infinity of possibilities.
And look, this isn't just some abstract philosophical hang-up. This is a massive practical problem in physics. If your final calculations depend on the coordinate system you just happened to pick, then you're not describing reality at all. You're just describing your own description. So the million-dollar question is, how do you cut through all that noise to find what's objectively, unshakably true?
Christoffel's answer, and this is the unifying idea behind all of his work, is that you don't just ignore this abyss of descriptions. No, you build a bridge across it. And that bridge is a twist. Now, the twist isn't some static object. It's an active process. It's a rule, a procedure for carrying information from one description to another in a way that preserves what's actually real. And in the formal language of mathematics, this active rule is called a connection. So let's put a name to this whole idea. We call the problem the invariant gap. It's that space between the messy, infinite world of possible descriptions and the clean, compact set of things we can actually go out and measure, the real observables. The twist is the mathematical machinery that lets us bridge that gap.
All right, that's the big picture. But does this theory actually connect Christoffel's two legacies? Let's dive into his work and see how this plays out, first in geometry and then with waves.
First up, geometry. So, back in the mid-1800s, Bernhard Riemann completely changed the game by defining geometry as the study of curved spaces. Awesome. But this created a huge headache. Imagine you're on the surface of a sphere. How do you take a simple derivative? How do you know if a vector is really changing, or if it just looks like it's changing because your coordinate grid is warping underneath it? Your answer is basically nonsense.
And this is where Christoffel just has this moment of pure genius. In 1869, he introduces a set of correction terms. We now call them the Christoffel symbols. These symbols are the twist. They precisely account for how your specific coordinate system is stretching and bending, which lets you subtract that noise right out of your calculation. Suddenly, taking a derivative on a curved surface has objective, real meaning again.
And what do you get for all this work? Something incredible. Once you have this machinery, you can calculate a property of the space that is absolutely real and doesn't depend on any coordinate system you choose. It's curvature. The curvature is that invariant residue. It's the objective truth that survives the journey across that abyss of descriptions, all thanks to Christoffel's twist. Now, let's jump to the second pillar of his work. 8 years later, Christoffel tackles what seems like a completely unrelated problem in physics. Think about a complex material, like a crystal. Inside, you have this chaotic mess, a continuum of possible vibrations. So how on earth do stable, predictable wavefronts, like a shock wave or a sound wave, actually form and travel through it?
His solution, it was another kind of twist. He discovered an invariant rule, a simple mathematical condition that acts like a filter. This rule sifts through that infinite abyss of possible jiggles and shakes, and it selects only the very specific, coherent waves that are physically allowed to exist. It's the exact same principle. Find an invariant rule to pull a single concrete reality out of a sea of possibilities.
So you can see the pattern. But believe it or not, the story gets even bigger from here. This unifying idea didn't just solve some 19th century puzzle. It literally became the language of physics for the next 150 years. Let's see how.
And this is where it gets truly mind-blowing. When Einstein developed general relativity, Christoffel's math wasn't just a useful tool, it was the theory. Those Christoffel symbols, the connection, the twist, they literally tell planets how to move through spacetime. And their curvature? That is the gravitational field. The twist became a physical law of the universe.
And it doesn't stop with gravity. This exact same idea is the foundation of modern gauge theory, which is our description of all the other fundamental forces. The fields for electromagnetism, the strong and weak nuclear forces, they are also described mathematically as connections, as twists. And the field strengths we measure? You guessed it. They're the curvatures, the invariant residue. This pattern is universal.
Today, this principle is everywhere at the cutting edge of science. Cosmologists use it to talk about the evolution of the entire universe. Those gravitational waves we can now detect, they are literally propagating ripples of space-time curvature. And theories like loop quantum gravity are trying to build space-time itself out of these pure relational twists. This program is alive and well.
So all of this forces us to confront a really deep philosophical question. If all our descriptions are flexible and kind of arbitrary, what part of our scientific theories should we actually consider to be real?
The whole idea of the invariant gap gives us a really powerful answer. It lines up beautifully with a philosophy called structural realism. What this says is that what's ultimately real isn't the coordinate labels or the specific math we use. That's all just part of the noisy abyss of description. What's real are the underlying structures, the relationships, the curvature, the wavefronts, the things that stay the same no matter how you look at them.
So let's go all the way back to our initial puzzle. When you look at it through this lens of invariance, the wall between Christoffel's two great legacies just dissolves. His work in geometry and his work on waves were never really separate things. They were two powerful applications of the exact same program, to build the mathematical tools we need to bridge the gap between our descriptions and reality itself.
And in the end, that's what's so incredible here. Christoffel's true legacy isn't just some formula or a set of symbols. He helped us identify the fundamental mathematical object, the twist, the connection that lets us take that infinite, confusing abyss of perspectives and pull out of it one single, coherent, objective world. He showed us how to find the signal in the noise.